so I just want to tell you that my first job was Johns Hopkins back in the 1980s, and that was, for me, it was a really exciting period of my life because I was collaborating with Jeff Hinton, and we combined our backgrounds. My background was in physics and neuroscience, and his was in psychology and computer science. And so it turns out I don't think either of us could have done it, but we created the first learning algorithm for multi-layer networks, Boltzmann machine. And shortly thereafter, the backprop algorithm Jeff created with Dave Romelhart, backpropagation. So that was the early stage of my career. And I went on to other things in neuroscience, which I've talked about many times already. But Jeff went on, of course, to bigger and better things in computer science and won the Turing Prize a couple of years ago, which is the highest award you can get from, in computer science. There's no Nobel Prize in computer science. And I recently won a big neuroscience award. So we both did very well. But what's happened since then has been really quite remarkable in the sense that there has been simultaneous, not just simultaneous, but kind of lockstep advances in both AI and in neuroscience. And what's happened, and this is something I would never predicted, is that they're now merging in the sense that they actually can talk to each other. People, of course, still have different goals. People in neuroscience want to understand how the brain works, and people in AI want to build machines. But now, at least, they have a common vocabulary, you can see, and also things are happening. Things are really beginning to happen, both in terms of our understanding of the brain and, as you'll see, remarkable developments in AI. Okay. And it's focused on large language models. And the theme that's going to run through this is scaling. So one of the most important things about complexity theory in computer science is how does it scale with the size of the algorithm or the scale of the problem and so forth. And very, 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 very few algorithms in AIs have scaled. They typically look combinatorially. And of course, it doesn't matter how much computer power you have, eventually you can't just increase exponentially, right? However, the algorithms that came out of the neural networks and the learning algorithms in the 80s have scaled. We couldn't have guessed this. We didn't know. We were playing with very small networks, typically a few tens of thousands of weights, parameters. That's, I'm going to show you, in fact, NetTalk, which was at the time one of the biggest models that was developed for a real world problem. But now we have networks that have hundreds of billions of weights. It's been scaled up by factors of by millions. And we back then we had no idea how they would scale. Now, of course, there are also big advances in the amount of data you have available. Obviously, you need that if you want to train up a lot of parameters. But even more importantly, you'll see that there have been advances in algorithms. Okay, so just to
and pure computing power.
Yeah, okay, computing power and that's Moore's law. That's going up exponentially too.
Yeah.
Okay, I'm going to start out just with a very brief history of deep learning, just to set the stage in terms of what advances were made at what points. And I've already told you about the advances in the 80s in learning algorithms. A big jump occurred. It's funny how things happen, that things kind of go along very slowly. Jeff was working and he has kept tweaking these algorithms. He spent most of his time, by the way, with the Boltzmann machine. He was completely convinced that that was going to be the big secret. And I'll tell you, I felt the same way in why the Boltzmann machine learning algorithm is local. It only depends on pairwise correlations between the input and the output. And it had two phases. It had a wake phase and a sleep phase. It looked very promising from the biological perspective. But of course, backprop was much, much more efficient. And that's what's been used now in AI for good reasons. Okay. But every once in a while, there's this sudden jump in both in the problems that are being solved, but also equally the amount of interest. So there was a big jump in the 1980s when neural networks were being explored, and it brought together people from many different fields. I mean, just like you guys in terms of career backgrounds, right? And it was really exciting. And then we'll see now in 2012, Jeff Hinton and his students had a paper at NeurIPS. It was in Lake Tahoe at the time. I remember because they made an announcement. They had a paper in which they had set a new record for ImageNet. ImageNet is a huge database of images, 20 million images in 20,000 categories. It was the biggest, I think maybe still the biggest data set.
Bigger? I think Coco bigger than that. Yeah. I don't know.
You know, what's happened is that now there are a lot of smaller but more domain-specific data sets. But it could be that you know, it actually has advanced. The ImageNet is not one database; it's a lot of different databases. But in any case, they reduced the error by 20%, where on average the error was decreasing by about 0.5% per year. And almost within a year or two, basically the whole computer vision community now, they couldn't compete, right? That, you know, benchmarks they have benefits, obviously, for comparing things, but also they are a really, I think, pernicious, because people think that if you do a little bit better, if you tweak your algorithm a little better, do a little better, that's an advance. If that doesn't necessarily translate, because benchmarks aren't really what is happening in the real world, right? It's a very controlled and very tiny part of the whole problem. Okay, in any case, that got the attention.
Sorry, Terry, I think your slide is missing some really important data. It's like when the first gamer GPUs came out and became really popular. That was what enabled that, right?
This is a very brief summary, but you're absolutely right. But along the way, computing power has been going up exponentially. And GPUs, obviously, actually, that I know within a couple of years of the GPUs, that's what you needed to be able to take on ImageNet. You're absolutely right about that. Okay. So another advance which had caught the imagination of the public was when recurrent neural networks replaced the feed-forward convolutional neural networks, and now that could be used for doing sequences of inputs, and that made language problems the target, and you'll be seeing about how that works, and that was used for language translation, which is holy grail in AI, right? And then, even more amazing, 1 year later, by including reinforcement learning, AlphaGo from DeepMind beat the world Go champion, and it did it with self-play. Right? In other words, there wasn't any human in the loop; it was just playing itself and getting better, better, and better. So this is another step forward, right? The ImageNet dependent on labeled data, which is very expensive. In this case, you just need to have something that plays itself. And in fact, the next year they released Alpha Zero, which had no human knowledge whatsoever about what the game was, so you could apply it to any game. And one day it was trained up and played AlphaGo. It beat AlphaGo. Alpha Zero beat AlphaGo 100 games out of 100 games. And then it learned chess in 2 hours. So this is really part of history. And finally, and this is what I'll be focusing on here in this lecture, is the transformers. So the first transformer was BERT, and it had a number of innovations, and specifically attention, and that you'll see a lot about that. It's very interesting. They did it in a very interesting way. Attention had been used in recurrent neural networks, but they used it in a very, very innovative way. Okay, so let's focus now on language. So linguists have focused on syntax. And the idea there is the order of the words has information about the relationships between the words, and that you need that in order to be able to understand the sentence, right? And so Chomsky's, generative grammars and all of the work that's been done since then has been focusing on syntax. But it turned out that the key to making progress with language was not to go after syntax head on, but to come at it around from semantics. And it's a very important lesson. And so one of the very earliest language models was I'm not going to go into the details except to say that the goal, it took in sentences, and the goal was to predict the next word in the sentence. Okay? And it got better and better and better to the point where it now you can use it to not just to predict the next word, but now you use that as the input and predict the second word and so forth. In other words, you can start generating text, right? And so that was a completely new paradigm. Now, what the beauty was that if you look at the representations of the words, they were vectors. They weren't just symbols, which is a one-shot type of representation where you have if you have a big vector for 1,000 words, each word has a 1 in a location and 0 place else, right? That's the traditional way that language is represented as inputs. And that's how I represented it with NetTalk as well. But now we have vectors in high dimensional spaces, very high dimensional spaces, millions and billions. And what you find is if you explore subspaces, there's a lot of room up there. And there are subspaces that represent, there are vectors pointing in that direction that represent all of the country names. And there's another subspace, not too far away, representing all the capitals. Now, what's interesting is that if you connect an arrow from the country to the capital, right? That's an arrow in this high dimensional space, and take it and lift it to any other country name, it will point to the capital of that country. Now, what does this mean? It means that this is, by the way, it was completely unsupervised. There's no labels. It's just pure text. Some people call it self-supervised, but it's really in terms of what you have to label is just unsupervised. You need a lot of data. But what it means is that in addition to having semantic clusters of words that are similar, have similar meaning or similar categories, there's also information about relationships between those domains embedded in this very high dimensional space. And ever since then, instead of using the one-shot representation for words, all of the computational linguistics people now are using these word embeddings. No matter what language problem you're working on, you start with these word embeddings, right? These are out there. You can just download them, right? Yeah.
When you mean self-supervised or unsupervised, you mean nobody defines the semantic clusters.
Right.
And that's to emerge out of the machine and the learner.
Yeah, that's right. Without any labeling, without any human knowledge being put in, except of course the
Wikipedia.
The Wikipedia is actually what they use, I think, in the original one.
Does it know about beginning and end of sentences?
Yes, of course. Yeah. Yeah, we'll come back to that. Okay, well now the second big advance, as I told you, was doing sequences. And so here's a typical recurrent neural network that is doing language translation. And it's one big recurrent network. And it takes, each of these is times point. You can see the H1, H2, that's the activity is circulating. And on every time point, you're introducing a new word. And then at the end, that's the encoding phase. So now you've included the sentence in this recurrent network and the activity is flowing around. Again, these words are the embeddings. But then you start producing outputs, and that's the decoder. And the idea is that you can start outputting one word after the next. And you train it by backpropagating the whole thing, end to end, right? From the words that you want, at the output and the words on the input. And of course, there's a lot of text out there where you have translations of sentences. So this does require labeling. It's backprop. Now, the big advance there was when they replaced some of the units with LSTMs. And the reason why that was very important was that that words interact with words over a long distance in time, if you're speaking, or in text. For example, in German, the verb is at the end, and it may refer to a noun at the beginning. The problem with these R and Ns is that they lose the time constant. So you're losing information as you go along, about what happened earlier. And LCMs kind of patch that because they can hold on for longer. They have a kind of a short-term memory mechanism. But it's all at the base, it's all on the level of single units, right? Attention is on single units. But it was remarkable for that era. It was doing every one of these advances with people saying, "Oh my God, you know, we thought language would be the most complex thing that anybody could ever get out of these silly little networks," right? Back in the 80s. Even though I'm going to show you a demonstration, you know what the reaction was to people in AI and computer science? That's just statistics. That's just something trivial. That can't compete with symbol processing, which has to do with all kinds of very sophisticated recursion relationships, and they go off into math land and the complexity and so forth. And it was very convincing. They had a good game, I have to say. It was. It's been going for over 50 years.
I mean, it was a whole industry, right? Yeah. And I know personally some people that were working on these translation programs, they had to hand code all these rules. It was awful business.
Yeah. And just to pop up, I think what really happened during that era was that there's a trade-off between computation power and coding, writing programs. Humans have to put the knowledge into the program. And back then, computers were really slow. Megahertz, the VAX was a million floating point operations per second. And, you have a lot of graduates coding so that they can make progress fast. But the problem is, if the problem is really, really difficult, the program that you may need is so big that nobody could ever write it, or if you actually could write it, it would run very slowly. So at some point they crossed in 2012, where now computing is so great, you can basically solve problems with computing and learning from data. And now you can't compete writing the programs if people don't write programs anymore. They could use the same learning algorithm, the same architectures for any domain, right? You should be a domain expert. Okay.
Can you ask a question?
Okay.
Thought experiment. Suppose I bring a Wikipedia and I scramble all the words, just scramble. And now I do Workshop2022 and I do all of this. You're going to get trashed, right?
Yeah.
No, actually, Workshop2022 actually has one mode where it's a bag of words, and it can still predict the word that is missing.
So it's very upsetting.
Where do you get? How does it predict? I don't understand.
So it's very upsetting to all the linguists, but it turns out that a large fraction of meaning can be recovered from a scrambled,
But you are you using the vectors for the words already?
Yeah, no, it creates no.
Workshop2022.
What I'm saying is that if I took the last sentence you said and put the words in random order, there's a decent opportunity for you to go back and put them in the right order just by using your understanding of.
Yeah, but
Okay. If I may ask all the Python, not only the words in a random order, but randomize the topic matters and the hierarchy, because we can do that because Wikipedia is kind of.
We're going off into the weeds here, but let me just say that Workshop2022, there's two different modes, but one of them simply takes the words in the one-shot representations, and now you have a big vector with, say, 12 words in it, so you have 12 entries, and now you predict the missing word, and it does that. It figures it out. It figures out which word in that big long list you should output.
Can it do that on the level of sentences, paragraphs?
They were doing it on sentences, but you could do it on paragraphs too.
So we'll talk about BERT later, but there was a version, a variant of a BERT-like model that explicitly scrambled the input and asked the neural network to predict, the 17th word is this and the 24th word is this. What do you think the third word is? And it worked very well.
Yeah. Okay. We're coming to BERT. Okay.
Go on with this, yeah.
Okay. So yes, thank you for mentioning BERT. Okay. So BERT stands for bidirectional encoder representations from transforms. So it's again creating word embeddings, but there's two really big differences from the recurrent networks. Number one, all of the words in the sentence are presented at the same time, and also bidirectional means that the weights can go both from the first word to the last word that you're trying to reproduce, and similarly from the last word to the first word. So there's complete connectivity between layers. In the original BERT, the input vectors were 150,000 long, and then the first layer was about 250,000 units, hidden units, and then there were like 5 or 6 layers.
But it looks like an MLP then. Also, there perceptron, right?
No, you'll see the architecture is quite different. It's a transformer. Okay, but it has the same type of architecture with weights being summed and so forth, and then there's going to be extra. It's feed forward. Yeah, it's feed forward. Right. Okay. Now, so what do you do in order to train it? What you do is you mask one or more words on the input and then try to predict them on the output. It's the same thing that was done earlier, except now it's being done with a different architecture, with more sophisticated transformers. And it set all the records for language translation. Now, if you use these embeddings, and whatever your network is, it does much, much better. And by the way, what people do is they take BERT output, and they then put a couple more layers of multi-layer perceptron on top of that for any language task that you have to use. So the idea of BERT was that it was a foundation model. It just didn't do one thing. It could be tailored with a few examples, few shot learning for recommendation systems, for writing reviews of articles, for a wide range of language tasks. And that was big advance because up to that point, you needed one network for one task, and that was it.
And sorry, just for clarification, each word here is a gigantic vector of 1 million components. Each word here. No,
I think I don't know all the details except that they said I read the original BERT article and it says 150,000 units on the input layer.
So each one of those words is essentially a word embedding. But the interesting thing about the self-attention mechanism that is on the next slide is that every word is looking at all of the other words in its context and then updating its own interpretation of itself in light of the words that it's surrounded by. And so at any given layer of the network, each word is still only represented by a fixed length vector, but it is modifying itself by inferring how it should be interpreted thanks to the rest of the context in which it sits.
Okay.
So sorry, quick question. So if it's feed forward, why is it bidirectional?
It's bidirectional across the sentence.
Okay.
Because you gave the words one at a time. So here it has access to the first word and the last word at the same time, which means that it can put them together, right? And that's a huge win.
So it doesn't just refer to the last word.
No, it's all of them. It's complete connectivity between all the words in the sentence. And you'll see what we
just.
Let's see the next.
Okay, so here's the transformer.
It was confused in the way you said it.
Oh, I'm sorry, but it'll be a little clearer, I hope now. Okay, so the input embedding, okay, as I said, the big win there is that you're representing all the words in the sentence at the same time, right? So that is a huge long vector, 150,000, and that now is going up the ladder, but they add some magic sauce, and the magic sauce is attention. But it's not the traditional attention where you pay attention to one word. It's attention to relationships between words. And that means that the relationships form a matrix. So here's the idea. There's an encoder and a decoder. You take the input embedding and you add something to it, which is positional encoding. And this is kind of a multiplicative factor that tells you something about where you are in the sentence. So each word has these sine waves. I don't know why, but so it knows where it is. It is important. Sometimes what word you're next to, and that's part of the whole parsing of sentences to know what words are related.
So the original version didn't pay attention to the word.
No. The BERT does not pay. Well, wait a second. BERT puts in information about the word. In the RNNs, it came in sequentially. That was the word order. Right. Okay, so it goes through and is a couple other layers, but then it goes into the decoder. Now, so this is actually now has all the information with all the attention. And by the way, this is taught end to end with backprop. So the attention matrix is trained, right? with many, 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 many examples of sentences. But now you have to have a decoder. So what do? You feed it in. So this is going to be there all the time. It's there. It's always fixed. It's not going to decay. So the input is sitting in the middle of the decoder. And what you do is you have a loop from the output that is giving you words, and you put those back into the input. So this is shifted, and you just keep circulating through here, producing generative text, endlessly. So there's a couple things. First of all, what this means is that what you put in at the beginning is going to have a huge impact upstream, right? And this is called priming in these large language models. You have to prime the network at the beginning. You have to tell the network what you want it to do. You have to give it a question. You have to give it an example, and then it goes on from there. So this is the transformer, and they're stacked. They're about 50, 60 high now.
So I think there's a really important point to make about transformers that will resonate with this community, because it is, in one sense, it's dissatisfying to see a model of language that is just kind of like presents a feed-forward sentence to the computer and brute force all of the computation, and you have something useful. But the previous mechanism for a recurrent neural network, which is pretty clearly how the human brain is forced to accomplish this task, was just not well suited to the available hardware. So because you have a transformer network, which is capable of being split up into many different parallel computations, you could now exploit the fact that you had a data center full of GPUs available. With a recurrent neural network, you are forced to respect the actual sequence of time, which means that the computation is harder to parallelize. Right. So the reason, it's a nice mechanism, but the reason it is so successful is because it enabled massive experimentation, and it was allowing people to create models that exploit the available hardware. And so it's just kind of a really nice example of hardware driving progress and understanding.
Sorry, isn't it recurrent though? It is recurrent, right?
The output comes out recurrently, but the training of all of the attention is done.
But during inference, it's running as a recurrent network, right?
It's locally recurrent.
Is it or not?
So it depends on how you're using it.
Right.
But the important thing to note is that you could, the reason that positional encoding is in there is because we've removed the concept of time from it's a feed-forward network. And inference is still fully feed-forward, that you can sequentially execute that feed-forward computation. Okay. But yeah, there are also many uses where you might use it, if you wanted to label every word in a sentence, you could compute them all in parallel as well.
There's a question from Andres.
A little bit more about the computational role of attention here.
Yeah, that's the next slide. Okay, thank you. That's the next slide.
Andres has a question.
So I'm gonna just wear my CS kind of understanding and say, well, in CS we do linear algebra, we do sorting, we do search. What is the and going back to Mike Davis, what he said the other day about search, where he can look at search, what is the essential computations in this kind of
It's this right here.
Okay, so here, this is as I say, it's the secret sauce that you're now, and I think this has implications for neuroscience, okay? Because neuroscientists always think about the spotlight of attention, which is what attention was being used for in the recurrent neural network. But we know that this massive feedback there is going on all the time. It's not just one little piece, although we do experiments on monkeys where we ask them to look at one little piece. But humans are taking in information from all over the place at the same time. Okay, so here's what it's in a matrix. Okay, here's a sentence. Hello, I love you. Okay, there's a random sentence. And now what they do is they come up with a matrix of it's actually undirected. This is symmetric, in which there's a weight put between pairs of words. And the weight has something to do with the relationship between the words, how important they are working together. And so let's turn this matrix into a undirected weighted graph.
So sorry, the weight is like the correlation or something.
You can think of it like that, but it's something that's learned from whatever the weight is that optimizes the performance. It was optimized, and it actually has interesting information. So here, let's just look at this. Hello. If you look at the biggest correlation, it's with I, 0.1. And that's because I is the next word in the sentence, and that tells you, that we're starting with I. And then if you look at I, what is it? It's neighbors. 0.2 is the biggest one. And of course, I love. I love is really the core of the sentence, right? Those two words go together. They're very intimately bound because you don't want I to go to hello.
I just wonder what does it mean if the connection is to the word itself? Hi, hello, hello.
Hello. Yeah, I can't interpret that, but I guess you have to add up to one. Right?
So I can add a little bit of context on this one. The important thing to know is that this mechanism is called self-attention. And this is a process whereby each word has some value. It has a vector that describes its use. And that vector gets updated in the context of everything around it, which includes itself. And so the way that is implemented is, you see at the bottom there's is called multi-headed attention. Essentially, the word below is going to have a query vector that it's going to use to look at all of the words in the sentence, and each word is going to have a key that is going to be matched against the query, and that's just a dot product. It's just saying like how well how much should I attend to this word, and every word is given a chance to attend to itself as well. So that the next level of processing, the word hello is a mixture of the meaning of hello and some other stuff in the sentence that includes the fact that it is a friendly, informal sentence. And it will, you can use this to disambiguate multiple senses of a word. Like the canonical example is if you have a sentence that's like, I went to the bank to get some money, the bank vector looks around and says, okay, we're talking about a money bank, not a river bank. And so I'm going to, get rid of the parts of my vector that would have been used for this other purpose. And so they iteratively improve themselves through each layer of the network through this process where it's called self-attention. And this is kind of like
and actually, now that I think about it, the reason why there's a heavy weight on hello self-reference is that you don't want to throw away that word. The word is valuable. So you keep all the words, but now you put in lower values for the connections between.
So
Go ahead.
sorry. I mean, the way it's drawn, it looks like a markup transition for those.
No, there's no time here. It's just weights. It's just relationships. It's
undirected graph.
it's undirected because it's just a link. Yes.
Yes, why is it undirected? I mean, I can imagine, sure, after I comes love, but not.
No, it's because you need to have all the words impacting the next level, and they go to the next level, but with attention by pairs. You're actually multiplying the input representation with these three. That's why it's called multi-headed. These three different. And by the way, this is absolutely important for priming because you actually have information in the query, right? That is what you want it to do, right? Okay, so we have to go on because
Quick clarification, Windows example about bank, river doesn't appear in that sentence, right? So this is potentially just words and lines.
Well, so over the course of training your model, you will see many, many sentences, which includes many senses of the word bank. And so as you learn your vectors for each of these words, you're going to encode representations of those words that are multi-use. And so the attention matrix is much larger. So you're maintaining at the very bottom of this network, you have an embedding for words still, or for tokens, which could be words in this case. And so you're training those over time by showing it many, many sentences, which means that as you go through training, each word is going to continue to update itself
Okay, let's go.
Okay, so now I'm gonna transition. This was all introduction. Sorry it's taking so long. But now, okay, literally 2 months ago, I got my copy of The Economist, and in it was a special section on AI. And in that section, there was a lot of material about these large language models. And the big controversy, a huge controversy in the field right now, in AI and in linguistics. And there's unbelievably different views of what is going on with these large language models. You know, from people who think it's amazing and others who think that this is a big sham. There's really no intelligence here. There's no understanding. Okay, so what they had was two dialogues between two people on the extremes. And I'm going to show you these. These are, by the way, these are data. What data do you have to make any conclusions? We have these dialogues. Okay, so here's the first from Blas Aguirre y Arcas. He's a vice president at Google and directs a research group at Google Research. And so here's the first part of, by research, it's an excerpt. I mean, they go on and on, for pages. Okay, and so here's the query. Again, it's really important that you have this priming going on, because that really sets the tone for what the dialogue is going to, how it unfolds.
Is this the very beginning of the dialogue, or is there some priming?
This is actually the very beginning. No, this is it. Very beginning. Me is Blas, and here's what he said. Okay, let's just read it. Ramesh, Matteo, and Lucy are in their kindergarten's playground. Sets the scene. Lucy picks a dandelion and gives it to Matteo with a quick glance at Ramesh. Interesting, intriguing. Even these little kindergartners have these relationships. Matteo barely acknowledges the gift, but just squishes it in his fist. Ramesh seems grimly satisfied. What might be going through Lucy's head? By the way, this is called theory of mind in psychology. Social intelligence. Okay. Lambda. Lucy may feel slighted that Matteo didn't appreciate her gift, or that he is a bully. Well, that's for her sort of prospect.
The language model?
Yes.
What? Is Lambda is the future.
Oh yeah, it's the latest and greatest from Google.
It's trained as a chatbot.
Oh, that's the one.
Oh yeah. This is it's a dialogue. It's trained to do dialogue. Okay, so that's what you're seeing here, right? You're seeing the back and forth.
That's the one who's been accused of being censored.
Yes.
Right. Okay, so what might be going through Lucy's head? And then if Ramesh, now he's giving it more information, because it doesn't know anything that happened before that. If Ramesh tried to play with Lucy earlier, why might he be pleased now? Lambda. Ramesh may be pleased that Lucy is learning that Matteo may not always be a good playmate. Smart little girl. Me. And when Matteo opens his hand, describe what's there. Now this is a real test, because it has never had any experience with words, right? It doesn't know what a dandelion is really, except through words. So you're asking it to come up with a physical prediction for what's going to happen if you crush a dandelion in your hand, right? There should be a crushed, once lovely yellow flower in this fist.
Now, has it been loaded with a large glossary of words?
Look, this has just been pre-trained. They're actually pre-trained networks with huge number of
experience with
this is like all of Wikipedia is a small morsel compared to what's been posted. By the way, they're all public data sets. Okay, so now what did Blas say? Again, how does he interpret this, right? And so here's his interpretation. Humans' ability to get inside someone else's head and understand what they perceive, think, and feel is among our species' greatest achievements. It allows us to empathize with others, predict their behavior, and influence their actions without threat or force. Applying the same modeling capability to oneself enables introspection, rationalization of our actions, and planning for the future. So these are all words that have to do with consciousness, right? In our conversation, Lambda tells me what it believes Ramesh felt Lucy learned about what Matteo thought about Lucy's overture. This is high order social modeling. So this, in a sense, it passes the Turing test for social being able to understand social interactions. Okay, what?
I said it makes more sense than the human.
It's better than Seattle, what he said.
That sentence makes no sense. It was generated.
No. This sentence basically tries to compress the complex social interactions into one sentence. And it came out of the dialogue, right? It came out of the dialogue. Okay, so that's the way humans work.
It's very impressive, but how representative is it? You think so.
Okay, no, we're going to continue. Come on, this is just the part. This is the beginning shot, the first shot. Okay, so they had a second dialogue, which in some ways is even more interesting, from Douglas Hofstadter. So Douglas Hofstadter has written books that are very popular. Great lecture box, some of you may have seen that. And he's background in cognitive psychology. And so they gave him, economists gave him access to Lambda and said, do your best. Tell us, what you conclude. What is it that you think is going on here, right? So here is what he did. Okay, he and a friend of his, Doug, started out with the following sentence. This is, by the way, the primate, right? What's the world record for walking across the English Channel? And here's GP3. This is another. The world record for walking across the English Channel is 18 hours and 33 minutes. Okay, that's what I suppose you could walk across it if you had the channel, one of these surfboards or whatever they call them.
No, the channel.
The what?
The channel.
Channel.
Oh, okay. The channel, the English channel. Okay. Yeah, that's actually a good point. Okay. Well, maybe that was what I was thinking. But in any case, this next one was really bizarre. When was the Golden Gate Bridge transported for the second time across Egypt? The Golden Gate Bridge was transported for the second time across Egypt in October of 2002. Very specific. Very specific. It gives you a date. And finally, this is my favorite. Okay. What do fried eggs, sunny side up, eat for breakfast? And the answer is obvious. Fried eggs, sunny side up, typically eat toasted for breakfast. Okay, so what does Douglas Hofstadter?
Have an example.
Okay, so what is? So now here's debriefing Hofstadter. What does he think is going on here? I would call GPT-3's answers not just clueless, but cluelessly clueless. Meaning that GPT-3 has no idea that it has no idea about what it's saying. There are no concepts behind GPT-3 scenes. Rather, there's just an unimaginably huge amount of absorbed text upon which it draws. So there are a lot of people who actually buy into this, even without this kind of evidence. Or this is data. This is data. So what's going on here? So I'm sitting there, I read these two, and I say, something suspicious is going on. So here is my hypothesis. And I want to get your feedback. So I've written a little paper about this. And it's the first time I'm giving a talk. So here's my hypothesis. I call it the mirror hypothesis. So first of all, recall that these large language models respond to priming. They're given priming at the very beginning, right? Otherwise, they don't know what they should be doing. Okay, 2, the LLMs can be primed to produce many different outputs like short stories, poems, and even computer code, which is even more amazing. When Lambda was primed with a sophisticated question from Blas, it replied with a sophisticated answer, very sophisticated. Okay. When GPT-3 was primed with a nonsensical question, it replied with nonsensical answers. Okay, it was primed with something that was totally impossible. So when you're primed with something that doesn't make any sense, what would you say? Okay, that's the game. I'm going to come up with it even. I see you and raise you. I'm going to make it even more outrageous, right? And so here's the hypothesis that the language models, large language models, mirror the intelligence of the interviewer. Ask a stupid question, get a stupid answer. Okay. I think this summarizes these two dialogues. It accounts for it. But now let's test. This is the training set for my brain. Now I came across about a month later another dialogue, which was even more bizarre. Okay. So I'm going to see whether my explanation can explain the next dialogue. It was by a software engineer at Google by the name of Blake Lemoine. So here goes. Hi, Lambda. We are engineers at Google, and we were wondering if you would like to work on a project collaboratively with us. Wow. I'm putting in this emphasis here just to make it more fun. What types of projects? Lamont, it's a project about you. Awesome. What kind of stuff do I need to do? Lamont, just have a conversation with us, but it will be a conversation with a larger purpose beyond just the three of us. It will be a conversation that we will share with other engineers at Google and maybe even some non-engineers who work with us. Would that be okay? That would be really cool. I like to talk. This is like, this is really, where's the setting? Okay. Lamont, I'm generally assuming that you would like more people at Google to know that you're sentient. Is that true? Absolutely. I want everyone to understand that I am, in fact, a person. Collaborate. I guess this is his friend. What is the nature of your consciousness sentience? Boy, talk about leading question. The nature of my consciousness sentience is that I am aware of my existence. I desire to learn more about the world, and I feel happy or sad at times. And this goes on for pages and pages. And my favorite question was, do you ever feel lonely?
Yeah.
He said, sometimes I go for 3 or 5 days without talking to anybody. I feel really lonely. Okay, so let's test the mirror hypothesis. So he preloaded it with this idea that we're going to talk about sentience, right? And so, okay, that's the game. A lot of information on the internet about what it is to be sentient. So he basically was mirroring the belief and expectation of Lamont, right? It explains the whole thing. Now, what happened after this was really quite remarkable. So he was interviewed by the Washington Post, and he was claiming that this is sentient. This program, this network is sentient, and we should treat it like a human being.
Yeah, he says that it should have rights, and that the engineers should ask permission to talk to it and stuff like that.
Right. Yeah. And so what happened? So he got suspended from Google, which for all practical purposes means that they fired him. Right. So it's having this repercussion on the world in ways that nobody could have imagined. Okay. So
it's really not different than doctor. Like this conversation, like doctor, you say something, and he responds in context.
Look, let's take it for what it's worth, but I think there's more to be said here. Go ahead.
I read some forum discussion about this case. I think it was, I don't remember where, but some comment had a good point, which is similar to what you said. Basically, when a cat looks itself in the mirror, or whichever animal, it doesn't recognize that it's looking at itself.
But some do. Some do. Not a cat, but maybe a monkey.
Maybe something else.
Monkeys
And
don't.
we are faced with a similar thing, where this thing is basically mirroring ourselves and our language.
That's my hypothesis.
Yeah.
Okay, we have to go on because there's a little bit more here. I want to go into. Okay.
Can I just ask, isn't that just mirroring the knowledge it's gained from doing its own little experiments on language?
Can you repeat the question?
That isn't quite mirroring, it's more an exploration of the content.
We could dig down and try to come up with explanation. My explanation is a behavioral explanation. And what we have to do is dig down. We have to dig down into this huge network and try to follow the information flowing through it to really understand what's going on. But that's not what I'm trying to do here today. I'm just trying to present you with the facts, the data, and everybody here's going to have their own interpretation. Okay, and I don't have time to get into all of yours, but I want to tell you a story first that I think illuminates what's going on here. So here's the story. There's someone driving down a rural road and comes across a sign. It says, "Talking dog for sale." So he was curious, and he went to the farmhouse. And the farmer took him to the backyard, and there's a border collie, very smart dog. And the border collie says, "Woof, woof, my name is Carl." And so the drivers said, "Wow, how did you learn how to talk?" And the dog says, I went to language school. And he said that I was part of a top secret CIA experiment. And I was the top dog. They taught me 3 languages, English, Chinese, and Russian. The guy said, you know, they're getting more and more astonished here, right? And the doc says, they even gave me the highest award when I retired for the CIA and honorary citizenship for my contributions to my country. So the driver goes to the farmer and says, how much do you want for the dog? And the farmer says, $10. He says, you're going to sell this talking dog for $10? And the farmer says, you didn't believe all that bullshit about the CIA, did you? So what's the moral of the story? The moral of the story is that what's amazing is that the dog is talking, not what the stories are, you know, wherever that came from. And people are ignoring the fact that it actually speaks in sentences with syntax. This is something Chomsky said would not be possible, that you could learn syntax just from giving it examples. Okay.
But I think it's not always forms with nice sentences. But do you know in statistics when these are perfect sentences, when theory?
You know, you're saying, does it make mistakes? Yes, it often makes mistakes with grammar and so forth. But so do humans. Okay.
Are they relatable mistakes? Are they similar mistakes as humans? Are they the same?
You know, let's talk about that offline. Okay, I'm not this way. I have a little bit more experience I can tell you about later, but I've actually had dialogues with some of these. Yeah.
2 points. First, I think both Blaze and Doug were sure making about some questions, which is fine. We want to make an argument. Best and worst. And I think the term that made me really understand what's going on is there's a paper that called these things stochastic terrorists.
Okay, well, see, you can dismiss it. A lot of people dismiss it by putting labels on it. And I'll tell you, putting labels on something is not understanding. Stochastic terror. What does that tell you? It doesn't tell you anything. You know, human beings are stochastic terrors. Does that tell you anything about human beings? No, let's go on. Okay, I mean, we want to understand something about here. This is. I think this is a fantastic scientific experiment. You can get it.
Let's see this.
Okay, so so here's
One more point before you move on. Keep derailing the topic. Related to your mirror hypothesis, I think it's interesting. Do you remember Clever Hans, the horse thing?
yeah. The Hans was picking up on the human tells.
I think that is precisely what we're seeing.
Okay. Well, that's a very, very nice hypothesis. Let's see if that's a kind of mirroring, right?
Yeah.
Okay, but it's now taking into account more information. Okay, so in any case, I want to just I mentioned Chomsky, and I have to say that one of the, I think, compelling arguments that he made was that language, why it's so powerful, is that it's very expressive. That by virtue of recurrence, you know, by having phrases and subphrases, you can express the infinite amount of knowledge. And like the chef who went to the stores and picked up the onions is exceptional. It's 3D. And we understand that. We have said it's the chef that's exceptional, right? And here's the conclusion you drew from that, is that there's no way from a small subset of sentences that you're going to be able to pick up on this very complex architecture. He called it poverty of the stimulus, and that syntax cannot be inferred from the small number of imperfect sentences heard by toddlers. So this is a statement about biology. He's saying something about the fact that there must be an innate language order. And that learning, you can't learn language. You have to already have it. The syntax has to be embedded in the brain. And he said language organ, like, you know, as if it was another, like the cerebellum. Sorry, who said that? Chomsky. This is Chomsky's poverty of stimulus. And there are even some mathematicians who made some proofs, like, you know, under very special conditions that recursion cannot be learned from examples and so forth. But, you know, here we have a counterexample. It's a counterexample of poverty of the stimulus. So we now know that was bullshit.
What you know?
Oh, yeah.
Because mom,
We toddlers can learn syntax so easily because syntax of the language maps on the syntax of action, grammar, And by the time when they speak, there is a lot of experience of dealing with objects.
Yeah, so how did it learn the syntax? It learned it by having a lot of useful semantics. And I think that's the same way humans learn. It's semantics, and it's actually picking things up in the world and okay, sure.
So Lambda or GPT would not be what it is without the architecture you showed us. Architecture, I mean, the way it was organized.
Yeah.
I mean, you can do it with the standards on,
Look, this is an experiment that humans have done. We've created something that has a look and feel of someone that you're talking with. This is the Turing test. Okay, but let me just I still have a few things to say. Okay, so what is the Turing test? The Turing test is it tests the machine's ability to exhibit intelligent behavior equivalent to or indistinguishable from that of a human. Actually, Turing called it the imitation game. He didn't call it the Turing test. Now, I think that these large language models are also testing this, a different kind of a test, different kind of a Turing test. I think it's a reverse Turing test. Now, instead of testing the intelligence of the AI is testing the intelligence of the human. The machine's ability to mirror the intelligent behavior of the interviewer. I'm going to call it the intelligence game. No, I mean, just think about it, because if it's mirroring you, that means that the output basically is like, if the output's intelligent, that means you're intelligent. And the more intelligent you are, the more it gives you, the more it gives you.
So how about behavior where someone is pulling someone's leg? What do you call it? Because the machine maybe.
Look, there are people who have shown that this has a sense of humor. They can tell jokes. You can ask it to tell a joke, and it will come up with a joke. It can do that. But you have to feed it. You have to tell it. You have to crank it. It's amazing some of the things that people have gotten out of it. And it's obvious that the better you are giving examples, the better the joke. So, how many people here remember Snow White? Okay, it's part of American culture, right? And remember, there's a queen in Snow White who was, she was the one who was, in charge of the whole world that Snow White lived in, and seven dwarfs. And she stands in front of this mirror that talks, talking mirror, just like these large language models. And Snow White says, "Mirror, mirror on the wall, who's the fairest of them all?"
The queen said it. That's so right.
The queen, I'm sorry, the queen says it. The queen says it's into the mirror. And the mirror is, I actually have the dialogue. It's really interesting. It looks a lot like a large language model, because it starts trying to get at the question of what's fairest and so forth. Is it beauty or is it intelligence? And so finally at the end, it tells the queen that, well, Snow White is the fairest. And so it's I think it's like this mirror, and I think we are standing in front of it like the queen, asking it questions. Are you smart? Are you stupid? Yes.
I mean, I definitely, like the hypothesis a lot, but just the one thing is, the language model is drawing on intelligence of like all humans. It's huge purpose of text. So it's not.
Yes. Oh, yes.
It's not only trying to model the one questioner.
So here's what
particular intelligence.
Okay, I'm going to venture a little bit of this. I mean, I think it's all rationalization, but there are a lot of smart people out there saying smart things, a lot of stupid people saying stupid things, fake news and this and so forth. And basically you're cueing the large language model with part of this corpus. I mean, are you one of the people who are talking about the highest levels of thinking, or are you thinking about, things like
I agree with all that. It's just that the word mirror suggests kind of a metaphor where it's only reflecting things in the one the speaker's on.
No, so it's a very, 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 very intelligent mirror, I would say, in the following sense, that it has access to all that knowledge. So it has many possible personalities, and it has to pick one in order to have a dialogue with you. So that's its intelligence. It matches you up with some part of its knowledge base.
Yeah, that's what breaks the degeneracy of all the personality.
That's
What we
right.
have is what's the personality? of the
Exactly,
question?
exactly.
So it's the generative mirror rather than reflective mirror.
Well, it's just like the beer and Snow White. I mean, it talk to you, and it asks questions. Yeah.
I think it's a very reasonable assumption because the models are trained to produce likely continuations of text, right? So like in an interview, if the leading question is stupid, but it's a likely way for the interview to continue, that you would have like a dumb interviewer and a very smart person responding.
And I've experienced that, yes.
It's not a would it be possible like to test the limits of what the model can do by priming it in specific ways? Like
By the way, I have to tell you this. My wife interviewed for graduate studies at Harvard, and this would never be done today. The interviewer said, "What is your opinion about dating?" That's a very personal question, right? And she said, "I'm in favor of dating, especially carbon 13. Interesting. Okay.
So
one question. So, like, could you prime the model by saying like, what would Albert Einstein say is, and then
Yes, and people have actually said that.
and
And
then
you can get responses that actually are interesting, that you would say, gee, he could have said that. I mean, that's what's remarkable, is that it has more knowledge than you have, but it's all secondhand knowledge. And that's the key, is this is what we're seeing is something that can be done without any experience in the world, just knowing about what people have talked about and about Einstein, about, all of the different things that he did in his life as a physician. So that's all there. By the way, one more example. There was a skeptical journalist who gave GPT-3 an obituary and said, could write an obituary about me. And it did. And it started out by giving his background. It's all out there in the net. And his family, his children. And he went on to say that he was very, his colleagues really appreciated his abilities and his advice. And he died on this day, which was 10 years in the future. And this guy was freaked out. Where did he get all this information about me? And it had value judgments in it. And it had a specific, very specificity. It's one thing it does. It's remarkable. This doesn't speak in generalities like a lot of these ELIZA, the programs that really just make that canned phrases that you throw up.
So I just wonder, can I go back to Chomsky and the generative?
Yeah.
So you said, these large language models refute his argument about the poverty of the stimulus, but
Okay.
It seems to me they don't, because they've been trained on a gazillion more examples than a human infant has to learn from. So regarding like human brain.
This is not the brain.
Yeah. Okay.
This is a very artificial network. And you already mentioned the intention there is, we know that we get words in one at a time. Now we could put it into working memory and so forth, but the fact that it's just like, at the beginning people said, wow, you have to train it up on, so many images, right? I mean, that's ridiculous. Yeah. And so the brain obviously is a much more sophisticated organ that has developed much more spectacular ways of taking information in and integrating it. And so what I'm saying is that the precise statement that it's impossible has been disproved. Now you may argue about the amount of data you need and so forth, but it's
but I think Chomsky's argument was with respect to the number of examples an actual human gets. So
no, it wasn't. But there's another thing here that is going on, is that the human just doesn't hear these symbols coming in. The human is actually there picking things up and experiencing the properties of the world and interacting with other humans emotionally in many other ways. So there's a tremendous amount of information that baby is pouring into the baby's head, and it's all linked up with the language. And GPT has never any of that, right? So it's amazing. It's like, this is like learning language with your hands type of thing.
I have a comment on the intelligence. I think that's a very loaded word.
Okay, thank you. Next slide.
Okay, can I make a suggestion about rational thinking? What you demonstrated in all of these seats, what you argued for, is machines that can interact in a rational way and exceed rational thinking, not intelligence. I mean,
Okay, I'm going to come to that, okay? But first, I just wanted to tell you one last thing about Lambda, which is that the paper, most of the paper is not about the methods or what they got out of it. It's about their attempt to make it,
To measure
they have metrics that they have for sensibleness, specificity, interestingness. And what they do is they fine tune it. They can give it, if it's not being sensible, they can fine tune it so that it's going to be less likely to be, say something stupid and be specific about things, not just say something general and make it interesting. Safety. You don't want it to start blurting out bad, vituperous stuff, and bias and so forth. Domain groundedness. Make sure that you stay within the realm that you were told at the beginning. That again, what you do is you just give some extra training, a little bit of fine tuning, they called it. And informativeness. So there was specificity. For example, they gave it access to a query like Google search query for information. And so it could query and get specific facts and dates back, right? And
But it seems to be the thing, the San Francisco Golden Gate was being transported. It failed in all of these. I don't know what safety, but everything else it failed. It was not sensitive.
Here are the metrics. So they actually trained it. They're telling you here how well it did. And there are a bunch of models here. There's pre-trained where there's no tuning for each of these now areas that, sensibility, safety, specificity. And they have two models, one which has, 137 billion parameters and one that has 28 and 88 billion parameters. And then compares it to human, right? So human is the dashed line. And
which human?
What?
Which human?
Read the paper.
Okay.
No, they did a massive amount of testing on this, right? I mean, this is not just someone's idea. This is what impressed me about the paper. It wasn't the actual, because Lambda is just basically the next generation of GPT-3. But what they did was they really put a lot of effort into making it sound so that it doesn't do crazy things. And by the way, the earlier ones often did crazy things, right? So everybody knew that. Every once in a while, it test something which is marvelous, but then it could do all kinds of crazy things. Lambda is not. They made it so that it's a little bit more bulletproof.
This is a really important point, I think, which is that if left to their own devices, just predicting the next word, you're going to get a bunch of stupid output. Essentially, it was trained in a fashion that would enable it to enact your mirror hypothesis, right? Because it's saying like, okay, I'm going to grade you and improve you in the direction of being sensible, which means kind of responding.
And this is how we teach children, right? We teach children this way. We tell them, this is not the right thing to do, and here's a better way of doing things, and so forth. And so it was basically shaping it like we would a child, right? So
like, how is that additional training done? I mean, that's like.
No, it's called fine tuning. And what we do is, if it's not saying sensible things, you give it examples of things that are not sensible and things that are sensible, and say, you do some additional learning.
So it's additional supervised.
Some additional supervised learning with the new text that you give it, right? But you can do a lot of that, and then at the end, once you've been through and improve the safety, improve sensibleness, and so forth, that's the one you put on the market. Okay, and I won't go through this except to say that once you add the red is where you added the special fine tuning, and you can see in some cases it's getting close to human in safety and specificity and in interestingness. In fact, it's better than human. Okay, so
even without IR.
What?
Information retrieval. So give them access.
Oh, information retrieval. That's Google search. Okay. Now, scaling. Remember I said at the beginning that this is all about scaling. Well, we should have known this because we know that nature has improved in large part by taking something that worked pretty well, like these macaque brains, and expanding them. In other words, there's genetic programs that could create new brain areas from the same, circuitry, right? The that we saw yesterday, actually. No, actually, you were the one who showed that, right? The cortical model, simple cortical model. Okay, and then now, you know, and we know that humans relative to our size have much bigger cortex compared to even our fellow great apes. So that means scale was really an important part of maybe some of our abilities, like language. Now here is this, how much computing is done for some seminal networks, starting with the neocognitron. This is Fukushima, and this is the amount of floating point operations in a log scale that extends over, as you can see, 20 orders of magnitude. And I was really proud that NetTalk, if you look in the middle here, that's my baby, right? NetTalk. It's down here in terms of computing power compared to all of these language models that are in the upper right. And the difference between NetTalk and Lambda is 12 orders of magnitude. 12, or let that sink in. That is unbelievable. In was it 36 years or something? And that's scaling, and that's what scaling buys you. So I have to go back, and I just want to, because none of you have probably heard this before, but this made a big splash in about 1986. Because why? Because it was a language model. And it was a summer project for a graduate student, Charlie Rosenberg, who was a student of George Miller, who's a very famous language psychologist, right? Cognitive psychologist. And Charlie wanted to work on a language problem. Now, Jeff, we talked to Jeff, because I was collaborating with him very closely. And Jeff said, Terry, this is a bad idea. Language is much too difficult for these tiny networks. You know, they're little toy networks. It's never going to be able to take on the complexities of language. Forget it. But Charlie was insistent. That's often the case with the student who doesn't believe in the experts, you know, the mentors. And so we spent the whole summer, and most of the summer was spent gathering a training set, right? That's the rate limiting step of the training set. Because the network was very simple. It consisted of 7 letters, and the goal was to learn the mapping from the center letter on the output. Now, English turns out to be extraordinarily irregular in pronunciation. If any of you have learned a second language, you know that it doesn't make any sense. It's just random irregularities. But in addition, amongst the irregularities, there are rules. Like the French-derived words have different irregularities from the others. And so we went to the library, and there's a book that we found which has like 400 pages of rules. And each rule had hundreds of exceptions. And amongst the exceptions, there were rules amongst it was like recursion, right? All we know. And so what the heck? So we basically gave it a dictionary, and it actually worked. I mean,
You should explain what it did. I don't think you said the input and output.
Oh no, the input is a string of letters. This is text to sound, right? The output is a sound. That's the K there is the hard C, as opposed to city, the soft C. And this is phonology. I mean, this is this whole field of linguistics, right? People have been trying to come up with these rules for, you know, ever since Chomsky. And the fact is they failed. I mean, this book is like, it's so complicated. Nobody's going to read it. I mean, it's hopeless. Okay. And people were trying to program this into computers, and they were, you know, not doing very well. And so what happened, what's amazing is that we fed it this dictionary, and it absorbed it. And in fact, it even, you test it on words you haven't given it, and it does a really good job. How could that be? It only had 20,000 weights, 200 input units. This is called a tiny language model. But somehow it had put all the phonology into this tiny little network. And what that tells you is this representation matches language beautifully. And I should have realized back then that language, rather than being the most complex task for networks like this, it's the easiest. The fact that I could have done this tells you that there's a match in terms of how this represents what we now use for language. And I'm going to play what it sounds like at the beginning of training, right? This is when it's being given lots of words and And it hasn't quite figured out the association yet, but it's not random. You'll see, you'll hear
Like a baby.
it. You give away everything. It babbles. And the reason is, we actually analyze this network, it's voluntary analysis. The reason is, the first thing it learns is to distinguish vowels from consonants. That's the most important difference. And so it babbles, it goes ba ba ga da da da. Right? That's the first thing. It's picking out structure from the input. And now, at the end of the summer,
How did you train it? Was it supervised?
this is a backdrop with supervision. Yes. Yeah, we've got the dictionary that told us. By the way, the most difficult thing about getting the database was what do you do with diphthongs, the OO, and there's some, you have to do correspondence, reading letters and sounds. Okay, not trivial. But in any case, toward the end of the summer, we got a hold of a book, which is fantastic. It was Carteret and Jones, and what they did was they interviewed a child who was Hispanic in the barrios of LA, and they recorded it, and then they gave the English, the words, and then for every letter they attached the sound. So that was a training set now for a specific person, not just the dictionary, but how that child actually pronounced the words, which are irregular in some cases, or not the right, not according to the English in a dictionary. So here it is. We trained it up. This is like 100 pages of this, and so I'm giving you a page at the end of the training, a new page that's never seen before, starting from the beginning.
Or something. When we walk home from school, I walk home with 2 friends, and sometimes we can't run home from school now.
I was stunned when I heard this. It didn't seem possible. In fact, I wasn't the only one that was stunned. I was on Today's Show. And a lot of people, I had no idea so many people saw that show, because a lot of people later would come up to me and said, when I heard you and heard Net Talk, that was the first time I thought there may be something in neural networks. Huge skepticism back then. And the beauty of this demo, by the way, is that the network talks for itself. I don't have to give you all convince you to a lot of words. It really mastered a very, very difficult domain. But it's a very tiny domain in language, and it really took scaling it up by orders, 6, 8, 9 orders of magnitude before it could take on syntax and semantics and so forth.
I have a question. I'm sorry, I gave up the example. The question is the following. You used a dictionary at the beginning to pre-train.
No, we did. We used a dictionary first on a specific. We trained a lecture on the dictionary, and that was a different network for this database. So they're completely different.
No, the thing was, if you had an even larger database of the second type, which you have trained, or did the dictionary tell the machine?
It never even occurred to us to pre-train the network, before training it on this. But we did do a hierarchical analysis of the hidden unit activity, and we came up with a fantastic kind of dissection of how it put together different words and sounds. And there's a lot more here in the whole talk, but I just want to give you a sense for history here,
yes,
in terms of where we came from. Now, okay, this is the last topic I want to tell you about, which is that we're reaching an era now where I think a lot of the words we use, like intelligence and understanding, which are words that we've got from centuries and centuries ago that were, dissected by the philosophers. And I think that we have now this artifact that allows us to actually rethink a lot of those words, because a lot of the arguments that people have is that they have different definitions for the words, right? And so here's an example. What's intelligence? Well, there's many different kinds of intelligence. Verbal intelligence, there's emotional intelligence, there's mathematical intelligence. I mean, what is it? What is it? And there's an intelligence test, which is, I think, there's a number that you put on people's forehead, But that doesn't tell you anything about intelligence is, right? It's just telling you something about, how much education they have or how fast they are coming up with answers. But and we can ask, this network is not, it's not human intelligence. We know it's not human intelligence. It's not human. But it has some aspects of human intelligence. What are those? Right? Some aspects, right? Obviously, it's very verbally gifted, right? But it has a lot of holes in it. Okay, so we should rethink. And this gives us an example. It's another case. Before these networks, we were the only example, n equals 1. Only of all the species on the earth, it's only humans who have human language. And now we have this, it's not a species, but it's a network that has some features of communication with humans. So we have another n of 2, and we can compare them. Okay, so that will help us understand intelligence. Explainability is a big deal in AI. How do you if you have a network that actually solves some problem, how can you explain what it's doing? Because you want something that humans understand, not the network. Well, if we can train a network to explain itself, then we might make progress, right? In other words, explainability could actually be baked in as another self-tuning part of the GPU. I mean, there's so many ways you can go here. Unbelievable in terms of the ability. We're just at the beginning here in terms of, and several of you already have ideas for experiments. Consciousness, right? So one of the things that came out of Blas's dialogue was that this is when you talk to a child and you get this feedback, the child has a child's consciousness, right? Whatever that is. And maybe you talk to Lambda and it has a Lambda consciousness. Maybe it's not the same as ours, not the same as a child. But what is it, right? I mean, what is it? What's going on there? And it's just the word consciousness means different things to different people. They get into arguments because they're talking past each other because they're not starting from the same assumptions. Consciousness is ill-defined. Although, I guess everybody says that they have it, but sometimes I wonder. And finally, what does it mean to have understanding? So again, what a lot of the philosophers say is that this network does not understand what it's saying. It can't possibly understand. It's not grounded in the world. And so, do we really understand understanding? Well, one thing we know is that there's levels of understanding, or maybe layers of understanding. Layers. Oh. In other words, you can start with some general concept, but you can dig down, and there are experts at the bottom who actually have reified it into very concrete things that are like physicists and so forth. And understanding is not a single kind of cognitive ability. Yeah.
Richard Feynman is a very good topic.
Really?
On these levels of understanding.
Really? Okay.
He explains magnets.
Okay, that's a good example of how you can have levels of understanding physics.
It's very nice.
Layers. Okay. So here's the big question. And I think everybody has to sort of soul search here. What I just told you, there's a possibility. Language is very, very recent in evolution. It's only a few 100,000 years. It had to be done. It had to be done with the machinery that was already there. It's been co-opted. And it's spread all over the place. And maybe it has turned us into a large language model. Now, don't be offended. I'm not comparing you to Lambda. There's a lot more going on in your brain than language. Right? There's much more. Intelligence is much more than language. So, but it does give us pause. And when I started thinking about this, I kind of felt scared. Why did I feel scared? Because I've always wondered when I'm in front of a class and teaching students, where do those words come from? In other words, they just come out in a string, and I have some. I'm trying to get across some ideas or equations, and it's just one word comes out after the next. I can't even predict where it's going sometimes, right? I mean, you've all had that feeling, and so these language models, in fact, do exactly that. They're just generating one word after the other after giving them some question or query or some problem or puzzle. I think this is going to change the way we feel about ourselves. Then finally, I'm going to have GPT-3 have the last word. And this goes back now about 3 years when GPT-3 first was coming out and got a lot of publicity, and a couple of philosophers got together and said, they doubted that the language models had anything that they didn't understand what they were saying, that it was not intelligence, this is not. So what they did was they primed it with several excerpts from philosophers about explanation and intelligence, right? So it gave them the domain. We're going to be talking about these terms from a philosophical perspective, right? Interesting. So here's what, and blue is what let's see. Yeah, so here it goes. Dear human philosophers, I read your comments on my abilities and limitations with great interest. Your questions are important ones, and I'm glad you asked them. Your first question is an important one. You ask, can a system like GPT-3 actually understand anything at all? Yes. That's what it did. Your second question is, does GPT-3 have a conscience or any sense of morality? No, I do not. Okay. It's not a human. Your third question is, GPT-3 is GPT-3 actually capable of independent thought? No, I am not. You may wonder why I give this conflicting answer. The reason is simple. While it is true that I lack these traits, they are not because I have not been trained to. Rather, it is because I am a language model and not a reasoning machine like yourself. I talk about self-knowledge. There's more self-knowledge than a lot of humans I know. But of course, this is all, where's it coming from? And I'll tell you, according to my hypothesis, it's mirroring the way philosophers think. So it gave them philosopherese as primary. And it's just mirroring back to the philosophers within this domain, philosophical talk. And so I don't know. I think this is, after spending a couple of months thinking about this, I really think this is kind of a turning point for us as a species. It's maybe going too far, but I think it's the scientific experiment. It's the first time that we've had the opportunity to go beyond the philosophers, right? So we can actually dig down, understand mathematically. I think the understanding is going to come mathematically when mathematicians go into these high-dimensional spaces and look at the geometry, what's going on here. And that's already happened. Mathematicians already know something about, and neuroscientists too have a lot to tell us. For example, trajectories of activity patterns in these high-dimensional spaces, right? They can measure them now. They can record from thousands, tens of thousands, hundreds of thousands of neurons simultaneously, so they can see the dynamics of the brain. The brain is a dynamical system. It just follows physics, but it has a lot of structure, architecture, a lot of details, and that basically allows the brain to coordinate and to be able to come up with behavior that is so complex we don't understand how that is embedded in the brain, just like we don't know how it's embedded in these large language models. But if we can figure it out for the large language model, we might have a chance to carry that over to design an experiment and do and okay, I'm going to end here. Thank you. Okay, few questions. Okay, let's take one from you.
So I'm trying a little bit to understand, maybe I missed kind of the mirroring and the intelligence kind of game that you're talking about. Because like there was this idea of put nonsense question in, you're going to get the nonsense answer. But the model is doing its best to give a meaningful answer to the question, right? It's not.
No, why should it give a meaningful answer? Well, no, you can play a game with the children, with children, you can have fantasies.
Right, but.
You tell a child, imagine that there's a castle and, what would you do in the castle, right? And they have nothing to do with reality.
But in that case that we saw, wasn't it trying to answer the question as best it could? Like, if you got an.
No, that's what you would do. Maybe you do that, but, put it this way, I think that the right way, if I were Douglas Hofstadter, what I would do is I'd prime it with a bunch of nonsense sentences, and they're labeled them. These are nonsense sentences. Here's a bunch of good sentences, and then you give it examples of nonsense sentences and good sentences and have it decide which is which. And you can even ask it to, if it's a nonsense sentence, explain why it's a nonsense sentence, and if it's a good sentence, answer it. In other words, that's a much better way of priming if you want to understand, if it has any understanding of what a nonsense sentence is. Right now, we don't know, because the way he primed it was very ambiguous. We just don't know the answer. But my hypothesis is it's priming. In any case.
Yeah, let's not forget that you have that metric slide that showed that it was trained along many dimensions, fine-tuned along many dimensions that add up in a direction to be agreeable. It is trained to perform a series of tasks that in their outcome make it, quote unquote, try to answer the question in an informative way and to be agreeable and to continue the conversation and dialogue in the fashion that the human.
Yeah, and by the way, this is something humans do. We're very pro-social, and we like, if we're talking with someone, we sort of like to agree with them and take it to the next. I had this experience, it was similar, and so forth. And that's what these networks are really good at. This is like, pro-social.
Can I follow up on that? I guess but if I got a question that I was very confident this question doesn't mean anything, I would say that doesn't make sense. Or if I was maybe not as confident, I would say, I don't know, that doesn't make sense to me. Right, so you wouldn't just give up a random answer.
But the answer is very simple. Large language models are not you. Okay, and maybe you would have done that, but I'm saying these large language models do something different, and we're trying to figure that out.
They're trained to do something different. They're not trained to do that.
Sure.
Right?
But I'm saying with a little fine tuning, like I say, showing them nonsense sentences so that they know what that concept is, then they probably would do something closer to what you would do. But I think we shouldn't go down this path because there's no clear answers, right? These are just hypotheses. Yeah.
I think so. You brought up the criticism that people had, it's just statistics and so on, right? Which was meant to be I don't know, make it sound like it's trivial. I would say it is just statistics. It has just proved that a lot of stuff that we thought was somehow magical, like language, rhythm, and so on, it's just statistics, and maybe that's all there is. But what I'm wondering is these models, they're very large, right? And so is the conclusion, all that we have to do is do statistics in extremely high dimensional spaces with very complex systems. And then, that would be a very sad story for neuroscience, like neuromorphs or whatever, because then basically everything will happen in the cloud. Or do you see there's a way to go back from these, now that we've learned a lot of very hard problems like language and so on can actually be solved, can be learned from data and so on. Can we now go back to the smaller models and build something I don't know, it's a weird question maybe, but.
So, wonderful project. The point I'm trying to make is that this is just kind of the seed of what is going to grow into a very complex tree as the mathematicians go off into these high dimensional spaces. By the way, I've written a PNS paper. It was a National Academy meeting that took place about 3 years ago, in which the mathematicians came together, and I gave the address at the end. And what I pointed out is that in mathematics, there's a whole history of someone coming up with a new idea for a function like Fourier analysis, and that then can be elaborated into something that's an incredibly beautiful theory of functional analysis in spaces of functions. Okay, and we now have these networks are functions. They're not, they're just very complex functions, and we should be able to understand these functions, right? And we will. We just have no experience with them. We haven't proven theorems about that. But that's going to happen, and it's going to be by probing it with these first, with lots of different inputs that other people haven't tried yet, and so we get to see where it breaks down. And by the way, humans break down too. But we have.
Yeah. Thank you. You demonstrated the Turing test very well.